Order versus molecularity. In this video, we're going to walk through and define order in terms of a particular reactant and overall order. We've sort of hinted at this throughout the previous videos. Now we're going to spend a bit of time actually talking about it with a purpose. We're also going to define something called molecularity, which we haven't discussed yet. And then we're going to explain the difference between order and molecularity because they're not particularly similar concepts, but they're easily confused if you aren't very diligent about thinking about what they mean. So let's talk about order of the reaction first. So this is some phrasing on things that we have already talked about. So let's say that we have a very generic reaction, which I have here, and we have a very generic rate law to go along with it, which I have here. If we want to talk about the order of things, here's how the phrasing works. For this reaction, we would say that it is X order in A. So X is the exponent on A, so it's X order in A. If that was A to the second power, we would say it was second order in A. If it was A to the third power, we'd say it was third order in A. And then for B, B is raised to the Y power, and so we say it is Y order in B. So if Y was equal to 5, we would say it is fifth order in B. If Y is equal to 1, we would say it is first order in B. And if we want to talk about overall order, we can do that too. You just add the exponents up, and that is what the overall order is. So let's do a few examples here to make it a little bit more clear. Let's take a random rate law. So we have A raised to the second power, B raised to the fifth power. The way that we would phrase this is that it is second order in A, fifth order in B, and seventh order overall. Let's look at another one. Here, we would look at this and say that it is first order in A because the exponent is a 1. Right? If there's no exponent listed, it's implied a 1. We would say it is second order in B, and that is third order in C. If we add all of these up, we end up with the sixth order overall. So this comes off the rate law and is usually experimentally determined. It's very different than what molecularity is. So with molecularity, this is a theoretical concept that is based on collision theory. So think back to our very brief introduction on collision theory, and this was the idea that molecules, in order to react, must first collide. So this is the number of colliding entities that would be required in a given step. Notice I don't say a given reaction, I say a given step. So we have multiple step reactions, which we've talked about. This would have a different molecularity for each step. So let's look at the examples I have here. We have 3 options that we're going to list here, which is unimolecular, bimolecular, and termolecular. So unimolecular is if you have just one colliding entity, or in other words, it just reacts on its own. Bimolecular is 2 colliding entities, and termolecular is 3 colliding entities, which is far less common. So here I have a 2-step reaction. It's effectively A plus B goes to D when you look at the overall reaction. But we have 2 different steps. Our first step has A plus B going to C. That has 2 entities, and so it is bimolecular. The second step has that intermediate C reacting on its own to form D. And so it's just one entity, and therefore it is unimolecular. Now let's look at the same reaction and compare the order with the molecularity. So remember, our molecularity is theoretical based on collision theory. Our order is an experimental concept based on the overall rate law. And so if I give you a rate law for this, I say this was experimentally determined to be A squared B to the 5th, it would be 7th order. Okay? So one last time, wrap up. We have molecularity versus order. Molecularity is a theoretical concept based on collision theory, while order is an experimentally determined rate law. And rate laws are going to be for the entire reaction, while molecularity is for each individual step.